Hi, my name is Szymon Łęski. I work in Allegro in the machine learning research team. Today I want to tell you about smart keyboards and language models. This is something I worked on in the previous company, which was Samsung R&D in Poland. If you think that one day you will work not only on research problems in machine learning, but also on actual products using machine learning, this will be very relevant for you. I will talk about things which are necessary to take your machine learning project from the research stage to a stage when your project is ready to be a part of a commercial product. In my talk, I will first talk a bit about smart keyboards, smartphone keyboards. Then I will talk about language models in general. And then we will take a look at the whole pipeline of collecting data, training the model, and deploying it on mobile device. And we will take a look at each of the parts, and we will wonder what are the challenges and what can we think of to make this better. Okay, so let's get started. We all use smartphone keyboards, right? Despite the popularity of voice interfaces, of speech recognition, there are still situations where we want to use a keyboard on our phone, and we expect this keyboard to be smart, right? We now expect functions such as word prediction, word completion, and error correction. And these functions are implemented in smart keyboards, and they can really help. For example, and they are really non-trivial. It's, for example, with word prediction, you can type faster. The same with word completion, and with error correction, error correction can help you type without making too many typos. And these functions can be quite sophisticated. If you take a look here, the text typed on the phone is Happy New Year, and each word is a correct word, right, in English. But we know it's not what should be in this context. And the suggestion here for correction is Happy New Year. And to achieve this, we use language models inside, essentially. But also, I said these keyboards can be quite sophisticated, but also they have sometimes they have a very bad behavior, right? We all know all these jokes, like autocorrect corrected something I wanted to type to something completely off. So I will tell a bit what to do, not to do this. Okay, so that was about smart keyboards, and now I wanted to tell you a few words about language models. So essentially, a language model is a function which assigns a probability to a sequence of words. So if you have a sentence in English like this, it's a completely proper sentence in English. You would like it to have a high probability. For this sentence, well, it's less likely than the elephant is walking in the bedroom, not the cat. So probably this should be a bit lower, but it's still a valid English sentence. And here, it's just a collection of words with no correct order. So we would like the language model to assign a low score to this. And the language models are useful everywhere where you have to choose the right word or sentence from a list of candidates. Then you can score them using a language model and choose something which has a high score. To be more specific, they are useful in such applications as speech recognition. For example, if you want to distinguish some words which sound maybe similarly but have a different meaning, and especially some if they don't fit the context. you can eliminate such candidates. The language models are useful in text or handwriting recognition, where you have some words which are maybe typed similarly, like here, and in machine translation to choose which translation is better, or maybe also in text generation using some algorithm. And what I said in typo correction, in text input prediction, these are the applications we are mostly interested in today. And what I will not be talking about is the whole other area of applying language models, which is transfer learning. So essentially, with these fancy models like BERT or GPT, you can pre-train language model on a huge data set, and then you can transfer this this knowledge of language structure to another NLP task. So this I will not be talking about, but I will focus on these applications in mobile keyboards. Okay, so let's now take a look at what it takes to make a language model for your smart keyboard. And there are essentially 3 steps. First, you need some resources, data. Then you need algorithm, so your actual language model. You need to choose an algorithm and you need to train it. And then you need to package your language model in a keyboard engine, which will be deployed on device. And at each step, you need to evaluate whether you're doing a good job or not. So we will now take a look at each of these steps and see what are the challenges involved. Let's start with data. So this is a simplified picture. You need more language resources to build the error correction and prediction engine for a smart keyboard. But these are the 2 most important components. First, you need a corpus for training your language model, which is just a raw text. So this is just text unlabeled. And usually the more text you have, the better it is. So essentially you need several gigabytes of text, which is a lot. And what is really important, you need it to be the right language. And I don't mean that if you're building keyboard for Polish, you need the text in Polish. I mean, that's also true, of course. But by right language, I mean in ideal situation, you would like your corpus to reflect what the users will be typing on your keyboard. Let me give you some examples of what may go wrong. For example, if you think about it, that you need a few gigabytes of text, the first thing that comes to mind is to crawl internet and just scrape some web pages for text in given language. Let's say you do this, but you mostly download newspapers, Wikipedia, this kind of text. For example, if you do that in Polish, you will have very few words, which are very few verbs, which are in second person, like, would you do something? This almost does not exist in newspaper texts in Polish. And then this is very typical use case, right? If you write a text message to someone, would you buy something on your way home? So using just news is not good. Probably the best thing you can do would be to target blog posts or Twitter, because this is more less literary language, I would say, more informal language. What we did when we worked on smart keyboards, for example, we used a bit of text from subtitles. But this is also tricky, because the language in the movies is not the language you use every day. There are a lot of movies about crime or gangsters or drugs, for example. And then you can end up with pretty funny suggestions if you use this corpus to train your language model. This is not an easy topic. There is last year there was a 30-page research paper on mining, analyzing, and modeling text written on mobile devices. So if you're interested, you can take a look at that. And the other major component you need for your keyboard is a vocabulary, which is a list of correctly spelled words. This is needed for error correction. And this is, this is essential because there is nothing worse in mobile keyboard than when autocorrect types, corrects what you wanted to type to something which you didn't want to type. Like too aggressive autocorrect is the worst sin of mobile keyboard. And you need to think, how will you get this list of correctly spelled words, especially if you work on multiple languages, right? Because if you just use text crawled from internet and take this as a list of correctly spelled words, well, good luck using this for error correction. We all know how text on the internet looks like. You need to really think about whether you're going to buy a dictionary of some language, or whether you want to hire people to construct such a dictionary, or maybe you want to use some unsupervised methods and machine learning to try to come up with a list which is good for this purpose. Okay, so this is about data. And now let's talk about algorithms, how to build a language model. As we said at the start, the language model is a function which assigns a probability P to a sequence of words. So without losing any generality, we can rewrite this as a product of probability of the first word, then second word provided the first, and so on. And we can assume that words which are close in the sentence are more statistically dependent. And we can approximate this probability by something simpler. So this is called n-gram language models. And if we just assume that each word is completely independent of other words in the sentence, we get a unigram language model like here. If we assume that the probability of the word only depends on the preceding word, we have a bigram language model. So, for example, probability of the word 3 conditioned on words 1 and 2 is approximated as probability of word 3 conditioned on word 2. To train this language model, we just need to count occurrences of n-grams in our corpus. For example, this probability of some word conditioned on its 2 preceding words will be just a count of all 3 words occurring together divided by the count of the 2 preceding words. So these are n-gram language models, and they are used with great success in such applications. They have some good things, which are they are fast. Like inference in such model is just looking up the value of word counts in some table. And but they also have some cons. One of this is that if you go with n too high, so you use n-grams with large n, then many n-grams will not be present in the corpus. So, which means you are restricted to a relatively short context, to a relatively small n. I think in commercial applications, you rarely go beyond trigram language models. And which is maybe more important, and I think very interesting, is that word similarity is not taken into account. So if you count occurrences of these words in the corpus, they're just separate words. So if you count cats in your corpus, it will tell you nothing about dogs. and we would like our model to generalize over word similarity. And as you probably know, if you are interested in NLP, a way to do this is to go from sparse representations of words to dense representations. In sparse representation, each word is represented as a one hot vector. So two different words will be just two different entries in the vocabulary and will have nothing in common. So for example, these two sentences, which are a bit similar in the meaning, which are quite similar in the meaning, essentially. The only word they share is in. So they will have very little in common in this representation. And the idea is to represent words using much shorter vectors. V is the size of the vocabulary here. But in such a way that similar words will have similar representations. So this is a crucial step. And this is used in neural language models, where words are fed into neural network. In this example, it's a recurrent neural network, and at each time step, you feed one word to this model. And then after each time step, you get a probability distribution of the next word. So this is what I think is probably the most typical language model used in modern smartphone keyboards. It's probably some LSTM or GRU recurrent network using words as units. Since we use these vector representations of words, then word similarity is taken into account. Also, these are recurrent networks with many steps, so they possibly use longer contexts than n-gram language models. And overall, they are a huge improvement over n-gram language models in this kind of applications. But they are harder to train, and they are more costly to evaluate, especially on the mobile device. Let's take a look at what they look like in more detail. So typically, such model has some layers or layers for word representation, which is the word embeddings. There is a recurrent layer, and there is a softmax layer, which outputs a probability distribution over your vocabulary. And this allows you to choose to score the sentence. And with each time step, you add such module. So this is the typical architecture of recurrent network-based language models. Now, imagine you run this on a smartphone. These two layers are quite heavy. They take a lot of memory, because if your vocabulary is maybe 100,000 or 200,000 words, then these are really huge matrices, which take a lot of memory. And you would, in order to fit your model on a smartphone, you would like to make these layers smaller. So one option would be to use a smaller vocabulary. But this also means your model will probably give less accurate predictions. Another option would be to maybe use a character level language model or subword language model. But the difficult thing here is that if your model does not have a fixed output vocabulary, then it can generate words which make like pseudo words which make no sense, or maybe it can generate some words which are offensive, or and you will have a hard time controlling this, which is important in a commercial product. Certainly, you can use quantizations, which is reduce numerical accuracy of your computations. You can use some matrix factorizations, maybe to represent these huge matrices as a product of smaller matrices. Maybe you could use specialized architecture. There are some recent works on adapting BERT for mobile devices. I didn't talk about BERT because it is essentially too heavy and too slow for this kind of applications. But maybe in future the smartphones will be fast enough, and the progress in making the architecture faster will be good enough. Okay, so that was running the language model on device. And let us now talk briefly about evaluating your keyboard engine. I'm saying keyboard engine because it's not only the language model which you want to evaluate, but also the how you use it to generate next word predictions, and how you use it for contextual error correction. For language model, you typically use perplexity, but this is maybe not such a good measure for your final keyboard engine, because even a low perplexity language model can give bad user experience if it's not trained on the right corpus. So you are better off measuring these things on the right, which are measuring how your engine predicts words and how it does error correction. So for next word prediction, you do next word prediction essentially to improve the speed of typing. And this is typically measured by how many keystrokes the user saves by using your predictions. But if you think of it, it's not the only thing that matters, but because you would also, maybe for a good user experience, you would also like to have diverse suggestions. This is something that my colleagues have explored at Samsung. And for error correction, you would like to correct typing errors, but you really don't want to change correct words into other words. So essentially, you want to go for high precision and recall, which is how many errors you correct, is less important. And that translates into the metrics you use, because if precision is more important, then maybe you should not use F1, which is just the harmonic average of recall and precision, but F.5, which is also a harmonic average, but one that weights the precision twice as high as the recall. Finally, I wanted to tell about this. If you use language model in smart keyboard, your goal is to have a product which is nice to use and the users like. There are many, it's really a puzzle of different things, because you need good performance of your model. You would like relevant predictions, and you would like your model to account for personal words of the user. You would like to have the model fast and small so that it fits on the mobile phone. And if you work on a team which does that, you probably work on multiple languages, and you have to consider availability of resources for different languages. And you have to consider the cost it takes to add new languages to your product. In research, what we focus on is typically just this part, which is the performance of your model. You want to reach state of the art. In applied machine learning, the goal is more complex. It is probably harder to achieve, but also, if you get it right, it gives you a really sense of accomplishment. If you can put all these puzzle pieces together. Thanks for watching.
All right, thank you so much, Szymon, and welcome here to the live. Maybe we'll go to the questions now. Cool. Maybe I'll start with my question first. So I was just thinking, how do you deal with having multiple languages? Do you concatenate it into one model in some way, or do you just have one model per language and it's not really possible to put it all into one?
That's a very good question. I think that traditionally you would just do each language separately, because, for example, you don't want to load into smartphone memory all the languages together. you need to keep it small and fast. But if you there are now keyboards which allow you to enable a few languages at a time. For example, I use English and Polish typically, and I think this loads two languages, 2 or 3 languages. But I think there are also yet like even newer developments which allow you to type in multiple languages without explicitly selecting them. But I think it's still done by loading just 2 or 3 languages, which were done separately.
Okay, thank you. And now the question from the audience. Do you know how big is the biggest model that could be used on a mobile phone? For example, in terms of parameters. How far are we from using models like BERT on a mobile phone?
I think you can run BERT on a mobile phone if it's not within a keyboard, because it will take a long time to process. In keyboard, you really need very low latency, because if you type, if you use language models for error correction, you run this model several times, maybe even 50 times after each word, because you want to evaluate many candidates and also many candidates for the previous word. So this really needs to be within one model run needs to be on the order of 1 millisecond maybe. But I think you can, if it's not for such real-time application, you can run. I don't know the number of parameters, but I think that maybe BERT base could be run. I mean, the modern mobile devices have several gigabytes of memory. I think you can run pretty large models, but if it's the only thing that the phone is doing.
Mm-hmm. All right, thank you. And we have one more question. Allegro has such model. Does Allegro have such a smart model? Sorry, once again. Does Allegro have such model with smart keyboard in mobile application? If so, what is your solution to make it light?
So no, Allegro does not, as far as I know, does not work on mobile keyboards. We just we have mobile applications for the Allegro service, and they use whatever keyboard is on your smartphone. So maybe if we enter the mobile phone business, but that's a joke, of course.
Sure. So thank you so much for answering our questions. Oh, there's one more question, sorry. You showed some methods of compressing neural LMs. Are there any methods for compression of n-gram models? For example, NISR-NI for big vocab plus high and have quite high memory requirements. Sorry.
This is a good question also. As far as I know, because these methods you mentioned, NISR-NI, these are for this allow you to sort of dynamically use higher n-grams whenever it's possible. And I know it's used in commercial applications. I don't know exact details how you compress them, but I think it's mostly using efficient data structures for storing the vocabulary, and I think that's mostly this. I don't know any other. Sorry.
All right, thank you so much. And